All right, welcome back. So today we're going to continue with this application of limits, namely finding derivatives of a function. And then we'll see how derivatives are related to the problem of finding a maximum value or minimum value that your function achieves. So optimization, that's a big application of derivatives. We'll look at continuity and what that means. And if we have time, I might go into epsilon and delta definition of limit, just so that when you see it in class, you're not shocked or freaked out. You're familiar with it. Okay, so last time we ended with talking about how a derivative of a function gives you the slope of a tangent line to that function at a point. So that's like a geometric interpretation of what a derivative is, a slope of tangent line. Okay. So using that interpretation, and this is really a question for people who have not seen differential calculus, right? Because I know anybody who has knows this answer. But first question, what is the derivative of a function which is constant? So its graph is a horizontal line. Zero. Okay, that is correct, right? If we take any point on the graph of this constant function, and you're asked to draw a tangent line, you'll just be drawing over that line. And it's a horizontal line, so the slope of that tangent line is zero. So we say that if the function is constant, its derivative is simply zero. Okay. So the derivative of any constant is just zero. Another way we can possibly look at it is to think of the derivative as a rate of change. So it's the rate of change. So derivative as rate of change of the y value relative to the x values. So here, if we take a change in x, so if we increase x by some amount, by what amount has y changed? Well, none, right? Because y is constant. So, and with that interpretation of derivative as a rate of change, you can also see that the derivative of a constant function is zero because it's not changing. Its rate of change is zero. Okay. So what about if your function is, is a line, yeah? So some slope times x plus some y-intercept. Okay, using the interpretation that a derivative gives you the slope of a tangent line at some point on the graph, we can once again see that if you take any point and you try to guess what a tangent would look like, you'd be drawing over the same line, right? So if our function has slope m, what would the derivative of that function be? M. This is correct. Okay. So those are two very basic, and also the rate of change, right? So if we want to interpret the derivative as a rate of change of the y values relative to the x values, we see that the slope would just change in y over change in x is exactly the slope of the line, right? And that's constant. So, all right. So for example, if your function is 5x minus 3, what's the derivative of that function? Yeah, it's just 5. It's just the slope because, yeah, it's a line of slope 5. Okay. Okay, so now we're going to revisit the definition of derivative. And we'll be looking at x, f of x equals x squared again. And now what we're going to want to do is kind of define the derivative for this function for an arbitrary x. So this is we're going to use a slightly altered version of what we did yesterday. So suppose x here is just a fixed point. And you want to know the slope of the tangent line at that fixed point. So using our idea of a limiting process here, we can choose another point. But this time, instead of calling it like some other letter, I'm just going to say that this point is just x plus some distance, h, well, plus some amount h. Okay. So that way we get, let me just use black here. You get a secant line. Okay. So what is the slope of the secant line? At the very top? Yeah, somebody asked me just to show that. I mean, we'll have this recording, great. Yeah, we'll have this up on YouTube as well if you need to revisit. Okay. So the slope of our secant line is okay. So this is the point x and x squared, right? Our function is x squared. This is the point x plus h, and then the x value squared. So the slope of the secant line is the change in the y values over the change in the x values between those 2 points. So we have the first y value minus the second one. And then we'll have one x value minus the previous one, the denominator. Okay. And of course, we can simplify that in the denominator. Okay, so now if I want our point over here to approach this point, what are we letting, what kind of limit do we have to take in order to get at the limit the slope of the tangent line? Right, so if we want the point with this x coordinate, x plus h, to approach this point with x coordinate, what kind of limit do we have to take so that we find the slope of the tangent line? So to get the slope of the secant line, we have to take a limit, slope of the tangent line. Okay, so we'll be taking a limit of this slope of secant line. But we're taking the limit as something approaches 0. It'll be the limit as h approaches 0. So you have to be careful here, right? Because all the examples we've done so far, we're letting x approach some number or approach or go off to plus or minus infinity. But here we're treating x as a fixed value on the x-axis because we want the slope of the tangent line to be a function of x. Okay, so to get the point with our x coordinate, with excuse me, our x coordinate, which is x plus h over here, to approach the point with the x coordinate here, we have to let h go to 0. That's right. Thank you for somebody that actually said that. So if we try to evaluate this limit directly, what happens? Well, as h goes to 0, we're going to get an indeterminate form. Right, because in the numerator, we're going to get x squared minus x squared. In the denominator, we have 0 as well. So that's indeterminate. Okay. So what can we do? Well, we can simply, we have to do some algebra. So what comes natural here is, well, just try to expand the numerator and see what happens, right? Now, with the, when you define a derivative using the limit definition, that's kind of what you expect. You expect to get 0 divided by 0, right? So here we're just going to expand the x plus h squared using binomial expansion. And something happens that we expect to happen, which is we're going to have the terms that don't have a h in them, they're going to cancel out. Oops, I don't know why I wrote that. Okay. And then we're going to notice that all the terms in the numerator have a factor of h. And this is something that's going to happen often, right? Especially with algebraic functions. So I factor out an h in order to more clearly demonstrate that we have a cancellation. Now remember, h is not 0. H is merely approaching 0. Okay. So now we are free to evaluate the limit directly. Okay. Evaluating the limit directly as h goes to 0, we're left with 2x. Okay, so it looks like f prime at x is given by the formula 2 times x. So if your function is x squared, its derivative is 2 times x. It's a new function. Okay. Now, I'll go ahead and give you the rule for differentiating x to any power. I'm going to go ahead and move on unless you have questions about this problem. We use the limit definition. And by the way, you in class, you use the limit definition of derivative to prove some derivatives are this formula, right? You'll have that on a test or something. But afterwards, after a while, of course, you're not going to use the limit definition. You're just going to use rules for differentiating functions. You're going to memorize a bunch of derivatives. Okay. So as it turns out, if you have a function in the form x to some power, and you use the limit definition of derivative, you'll come up with this formula. So if you're interested, you might want to look up something called binomial expansion. Let's just pretend that n is an integer or a positive integer. So you'd have x plus h to the power n minus x to the power n. So that's the change in the y values. And the change in the x values is what we're using letter h for that. And then we would take a limit as h goes to 0. And what would happen is that you would try to find a general formula for x plus h to the power n. And there is one, binomial expansion. Okay, so you can Google that if you're interested. But it'll turn out that, when you multiply this stuff out, you're going to get x to the power n and then you're going to get n times x to the power n minus 1 times h, and then some other terms which I don't want to really write down, but so just some numbers. Okay, it won't matter. We'll see why. Then you get h squared and so on until you get to h to the power n. So that would be the result of expanding this using binomial expansion. And then we have minus x to the n. Yeah, that's from over here. And you're dividing by h. Oops. Okay, so what would happen is that, of course, the x to the n from the binomial expansion and the x to the n that we had in the first place over there cancels. And now all your factors in the numerator have a h in them. Sorry, h goes to 0. So because all the factors have, or all the terms have a factor of h, you can factor one of them out. And that way we see that indeed we have a cancellation with the h in the denominator, and that's great, right? Because we will no longer have 0 divided by 0 when evaluating the limit directly. So now we let h go to 0, and all the terms that have an h in them will go to 0. So all the stuff just goes to 0 at the limit. And then notice that, okay, I felt it freezing for a second. Okay, so now notice that there's a one term that doesn't have an h in them. So when you take the limit as h goes to 0, it's unaffected. So you're just going to be left with n times x to the power n minus 1. So this works for any number, but for our purposes, it's just good enough to think of, let's say, positive integers for now. So for example, if your function is x to the power 5, according to this rule, and this is what I mean by rule, yeah, you derive the formula for differentiating x to the n once, and then you just use the rule that you derived. So 5 times x to the power 4. You bring down the power to get a coefficient, and you subtract 1 from the old power to get the new power. Okay. Thank you. Okay. So now let's look at one of the superstars of calculus and I guess math. Namely the exponential function. So we have e to the x. Now, what we're going to have to use to derive the formula for the derivative, okay, is a limit that we looked at yesterday, and I didn't really give much justification, which is okay, because it's a hard thing to do here. But the limit of this, e to the h minus 1 over h, as h goes to 0, is 1. So this is just a fact that we stated yesterday. So is h going to 0 because it is the addition of x. We're treating x as if we're a fixed point, right? And then what we do is we say, well, we're just going to move over some. The amount we move over is h. So we're at a new point, x plus h. Okay, and then what we want to do is we want this point to approach this fixed x. But that's equivalent to saying that h goes to 0. So point P moves to point Q, right? P goes to Q is equivalent to saying that h goes to 0. So I hope that answers your question. All right. That somebody had in the chat about why is h going to 0 when we take the limit. All right. Anyway, so let's use the limit definition. I guess maybe a picture might help here. Right, we have our exponential function. We're fixing x, picking a point. We're moving over some amount h to a new point that, of course, is going to be x plus h. And so we're going to get a secant line through the graph of our exponential function, x plus h, and then our exponential function for the y value. And this point would be x and e to the x. Okay, so the slope of that secant line is the change in the y values. So one y value minus the other, divided by the change in the x values, which is just h, right? It's the difference between x and x plus h. And then we're going to let our point here approach the first one by letting h go to 0. Okay, and so then we have to compute this limit, but there's no algebra that we know that will help. Let's try to evaluate directly. As you expect, you get e to the x minus e to the x over 0. So that's 0 over 0, indeterminate. So, there is one piece of algebra we could do, right? We could use properties of exponents there. And now e to the x is a common factor. So we factor that out. And now, of course, e to the x doesn't care what h does. It just stays e to the x. H is not involved in this factor at all. So it's unaffected, right? So we can just bring it outside. Okay. It's like a constant as far as h is concerned. But now we have this limit of e to the h minus 1 over h as h goes to 0, and we know that that limit is 1. Okay. So we just get e to the x times 1. Okay. So why is this exponential function so special then if you try to put it in words? So in your words, why do you think the exponential function is special in terms of calculus? So the derivative of the exponential function is equal to itself, yeah? And that's pretty special. And that's the only function for where that works, except possibly, I guess there's a really trivial, another function that it's equal to its own derivative. Can anybody guess what that is? And it's really a silly function. Can anybody think of a different function, a very simple function, which is equal to its own derivative? Well, yeah. So we said that the derivative of a constant function is 0. So if your function is equal to the constant 0, and we know the derivative of a constant is 0, that's just, but that's a silly example. It's a trivial thing. Yeah, so it's not interesting. Okay. So e to the x is special, right? It's equal to its own derivative. So when you're on your deathbed and they ask you, well, what do you remember from calculus for some reason? This is the thing you're going to remember probably, right? The derivative of e to the x is e to the x. I think I had a professor pay their kid, like a 7-year-old, $1 every time they repeated what the derivative of e to the x is. So I don't know. It's kind of funny. All right. Now, I'll go ahead and talk about another way of, well, this is more, I guess, historically accurate, maybe. So in math, people often think of these functions as having an infinite polynomial expansion or infinite polynomial representation. So they were doing this even before calculus, right? So if you wanted to design a function that's equal to its own derivative, you might want to write it as this infinite polynomial. 1 over x, sorry, 1 plus x over, I'll just say 1 plus 1 over x squared, and then 2 times 1 plus x cubed, 3 times 2 times 1. And the pattern that you see in the denominator, it's a very common pattern in math, and you will be seeing it. Does anybody know the name of this pattern where you multiply the first so many consecutive positive integers? Right, and this keeps going forever. It's an infinite polynomial, or if you'd like, series, as we call it. It's called, yeah, factorial. So just for a reference here, if I say 1 factorial, I just mean 1. If somebody says 2 factorial, then I mean 2 times 1. 3 factorial is 3 times 2 times 1, and you see the pattern, right? So that's something you will be seeing. So let's just pretend that, okay, that's the way we're going to define this exponential function. Then what would the derivative of this function be? Well, let's just this is not a geometric series. A geometric series wouldn't have that pattern in the denominator. A geometric series would be, I'll erase this really quick, but a geometric series would look like this: 1 plus x squared plus x cubed. Right, so there's nothing changing in the denominator. That's geometric. This is different. Yeah. Yeah. So this, and by the way, I guess I said the word, but let me, factorial. You see things like, factorial and probability in counting problems, like when you want to count, graph theory. Okay. All right, so let's just differentiate term by term, because you can do that. So what's the derivative of 1? It's a constant, so its derivative is 0, right? Okay. What's the derivative of x? Well, it's just if you'd like, if you have y equals x, that's like a line of slope 1, so it's just 1. What's the derivative of x squared? And so we have to use our derivative rule that we just came up with. So I'll just write it. So the some function is of the form x to a power. Its derivative is where you bring down that power to make a coefficient and subtract 1 from the old power to get a new power. Okay. So the derivative of x squared is just 2x, as we already see, as we already actually derived. The derivative of x cubed, bring down the power, subtract 1 from the old power, and so on. Okay, so this keeps going forever. Now we can simplify this. You get 1 plus, and notice all these cancellations here, right? You get, sorry about that. All right. So x plus x squared divided by 2 times 1, x cubed divided by 3 times 2 times 1. Okay, plus and keeps going forever. But what do you notice about this infinite polynomial? Well, it's exactly the same as the infinite polynomial that I told you about, I wrote down for, right, the exponential function. Exactly the same. And it's exactly, one reason, of course, is because this keeps going forever. So the next term will be like x to the 5 divided by 5 factorial. So beautiful. So indeed, this is exactly the same series that defines e to the x, or infinite polynomial, if you will. Okay. So you will be exploring such infinite polynomials or series expansions for functions, but in your second semester of calculus. So I apologize. I thought that was just a neat way of looking at the exponential function. Okay. All right. Great. So I think that gives you the flavor of how we define a derivative using a limit. Okay. And once we derive formulas, we just use those when differentiating in practice. Okay. And of course, the derivative of e to the x is e to the x. All right. So next, we're going to look at how derivatives can tell us something about a function, or what they can tell us about a function, right? So it's a pretty So this is the graph of some function. Okay, so I'll cut it up like along these kind of sections. All right. So in the first interval, let's call that the first interval here, second interval, third. In the first interval, is our function increasing or decreasing? So as x increases, is y going up or is it going down in the first section? Okay, it's increasing. So yeah, so as x goes up, so does y. So we say it's an increasing function. So we say f of x is increasing on this interval. Okay. Now, if you didn't have okay, so then what can we say about the derivative of the function on that first interval? So if you just take a point on the graph somewhere in that interval, and you draw a tangent line, what can we say about the derivative of f at x? Well, okay, is it going to be positive or negative? Is the derivative of first interval going to be positive or negative? It's positive, right? Because if a function is increasing from left to right, then we know that its slope or gradient is positive. Yeah, it's a climb uphill. So the derivative will be positive. And those are synonymous, right? So if we know the derivative of a function and we see it's positive, we know that the original function must be increasing. So you're gonna be using derivatives to say something about whether the function is increasing or decreasing somewhere. Okay. Now on the next interval, what can we say about our function f? Is it increasing or decreasing? It's decreasing, yeah. If I can spell that correctly. Okay. Yeah, it's good enough. So f is decreasing. So as x goes up, the y values go down. You're going downhill if you're traveling from left to right. And then also we see that the slope of a tangent line on that interval would be downward sloping. It's negative. So you're going to learn that a negative derivative for a function indicates that the original function is decreasing, and so on. For interval 3, of course, f of x is increasing. As x goes up, so does y, and the derivative would then have to be positive, as we can tell by the slopes of these positive slope of this tangent line. Okay. All right. All right. Now, what if we wanted to know in this picture, where does our function attain a peak, a maximum value, right? At the top of the hill. Okay. So it would obviously be here. I'm just talking about locally. I don't care what happens. Like, I can't cover it up, but just so nearby, that's the top of the hill. That's a peak. We say that that would be a maximum for your function locally. Okay. So this is a maximum for your function. So your function attains a maximum here. And then what can we say about the slope of the tangent line at that point? If we're at the top of the hill and you draw a tangent line, the tangent line has to be horizontal. Yeah, you'll get a horizontal tangent. Yes. So in this picture, at least, where our function attains a maximum, a peak, we see that the slope of the tangent line is 0. So the derivative will be 0. Okay. And exactly the same thing will happen at the bottom, or at a minimum. So at the bottom, so at the low point, your f, we say f attains a local minimum of f. And likewise, we see that in this picture, at least, it looks like the slope of the tangent line would be 0. We'll get a horizontal tangent. Okay, so that's very important, because one of the big projects in first year calculus and applications, I guess, is to optimize functions, in the sense of you want to find its maximum value, find some x which will maximize the function. Let's say you want to maximize profit, right? And other times you want to find a value of x which would minimize your function. For example, you might want to minimize cost of something. Okay. And so what this suggests is that if we're interested in where our function has a maximum or minimum, a good place to look, but it's not the only place to look, is where your derivative are the x values which make your derivative 0. Okay. So good places or good candidates for where for x's where your function attains a max or a min, or maximum or minimum, are where the x's which make the derivative 0. It's not the only way, by the way. And just because the derivative is 0 doesn't mean you're going to get the maximum or minimum. But this is a very important observation here. A lot of your problems will be find the maximum and minimum of this function. So you'll differentiate, and one of the things you'll do is set the derivative equal to 0 to solve for x, because that'll give you candidates for where the function indeed has a max or a min. Okay. Now, yes?
Yeah, sorry. So you were saying like the maximum and minimum values are for the local, right? But we can clearly see that the function reaches like higher than that.
Well, that's why I said local. That's why I said local, like only nearby.
Okay.
I mean, right? I mean, I guess if you're mountain climbing, right? You don't care that there's a mountain higher than oh gosh, did I freeze? Nope. You don't care that Mount Everest might be higher than the hill you're on, right? So here's Mount Everest. But as locally, if you're in the Rockies or something, you just care about the peak of the Rockies. You don't care about the peak somewhere else. That's why I said local.
Okay. Understood.
It's true. Another issue is actually to find where the function globally has its maximum value. Now, that's a different story. Okay. It's a related story, but
For a local function, are you setting like two ranges in the function and then saying at this point, like how can you determine at that particular, how do you determine which is local to you, to the
that's a great question. How do you know that it's a low? So a local max here, for example, this is Mount Everest, happens to be also the global maximum, right? So all right. So if you'd like, all global maximums and minimums are also local maximums and minimums, but not all local maxes and mins are global.
Okay.
But there's, I don't have one set answer for you about how you determine. Like in this picture, we can obviously see that um, our peak here, if I can get this to work, our peak over here and our trough over here, right? They're not global max and min, respectively, because we obviously, as you mentioned, the function takes on lower values and higher values somewhere else. But locally, that's sometimes all we care about. In practice, what happens is that you don't care about all possible x's. Does that make sense? You
Yeah.
only care about a certain interval, and so you can try to find the min-max in that interval. You don't have to think globally necessarily, if that makes sense.
That's what I was
Okay.
asking. Like for a local to determine it, you provide the interval of the function, and then you find where the derivative is zero of that interval.
Yeah. So you have an interval, and you want to find local maxes and mins on that interval. So you differentiate your function. You set the derivative equal to 0, and you solve for x. And you also have to consider the two endpoints of the interval, by the way.
Okay.
That's because you could attain like a minimum value at like the left endpoint here, and a maximum value at the right endpoint. Okay, so not only where the derivative is 0, but also for a closed interval, the endpoints of that interval will be important when checking for maxes and mins. Good
Okay.
observation. All right. Now, just a warning. So I said that if, well, just because the derivative of a function is 0 doesn't mean you have a minimum or maximum. It's just a candidate, as I said. So for example, this is the graph of the disco graph, right? The disco polynomial, the y equals x cubed. Okay. Let me just call that f of x so I can differentiate. Okay, so what's the derivative of our function, our formula? Well, we use that rule where we bring down the power, subtract 1 from the old power. Okay, so where is this derivative equal to 0? Well, it's equal to 0 exactly when x is 0, right? So that's the only place. So what that tells you is that at x equals 0, you indeed have a horizontal tangent, a tangent with slope 0. But as you can see for this graph, this point is neither a maximum nor a minimum value locally, right? Because just to the right, you can get bigger values for your function, and to the left, you can get smaller. So locally, that's not even a min or a max. Okay. So and you'll deal with that when you get to class, I guess. There's different tests you can use. Okay. I just want to get the basic idea of relating derivatives to whether the function is increasing and decreasing, and if you have a peak or a trough, your derivative will be 0 or undefined. Okay, that's a caveat, or undefined. All right. Yeah. So for example, if they say, now this is an easy problem. So this is our function. What's the minimum value of that function, even globally? What's the smallest value that f can have? Well, if you didn't know the graph of this function, you would try to find candidates. So you differentiate, set the derivative equal to 0, and you see that the candidate is x equals 0. So we think that at x equals 0, our function might have a min or a max. Okay, so what you'll do next, again, I'm pretending that I don't know the graph of the function. Okay, So what we can do next is say, well, that's 0, and that's where our derivative is 0. Everywhere else, our derivative is going to be positive or negative. Okay. So what you can do is you can take a test point. Let's say you take a test point to the right of 0, like 1. Okay, and if you plug that value of x into the derivative, you get 2 times 1, right? X equals 1. So that derivative is positive. So if the derivative is positive at 1, what does that say about the function at 1? Well, it tells us that it's increasing. So, and this would be true for any point to the right of 0, right? If you plug that point into your derivative, you're going to get a positive number. So we know that our function is increasing. F is increasing to the right of 0 because f prime is positive for x's which are positive. Okay. Now, if you take a test point to the left of 0, you plug that into your derivative, you're going to get that the derivative is 2 times negative 1, so negative in any case, right? And this would be true for any x value that's negative. You plug that into the derivative, you're going to get a negative derivative. Okay, so you can conclude then that since your derivative is negative, right, that your function is decreasing. So f is decreasing here because f prime is negative for all x's which are negative. Okay. So then, just looking at that, again, pretending you don't know what the function is, what it looks like, what can you conclude about what the function, whether the function attains a maximum or minimum at 0? What can you conclude? Yeah. Well, it must be a minimum, right? Because you're going downhill, and then you're suddenly going uphill, so you must have reached a low point. You're at the bottom of the valley there. Okay. So that's the kind of analysis you'll be doing. You'll find where the derivative is 0, and then everywhere else you choose test points, and you get a sense of whether your function is increasing or decreasing, and that will give you whether you have maxes and mins, right? If you had a function which was increasing and then decreasing, then you would have a maximum. If you have a function like our cubic, y equals x cubed, you see there would be a problem because your function is increasing to the left of 0 and it's still increasing to the right of 0. So we can't have we have neither a max nor a min at 0, if that makes sense. You'll only have a max if you're increasing first and then decreasing. All right. Anyway, so that's going to be a big part of your class, finding maximums and minimums of functions. And that also has lots of word problems involved, right? Because they might give you geometry problems like maximize the area of this rectangle, which is inside the circle, something silly like that. Okay. All right. Now, so optimization, big topic, first semester calculus. Okay. Now, before I move on to continuity, I did want to have a small interlude here because we talked about indeterminate forms, and I did mention one of them, at least one of them, but we already said that 0 over 0, right? If you start making a list of try to compute the limit directly, and you get this kind of stuff, 0 over 0 or infinity over infinity, we said that those are indeterminate forms. Well, there's a longer list. And one other indeterminate form that you might want to look at is, let's say, 0 times infinity or whatever, infinity times 0. Okay, right. So this is like you have two factors, and one factor is getting large, and the other factor is going to 0, and they're being multiplied. Okay, and so it's like the two things are vying. The thing that goes to off infinity wants to win, and the thing that's going to 0 wants to make everything 0, if you will, make everything small. And so you don't really have a sense of which factor wins out. So we don't know what this is. It's indeterminate. It's nonsensical, right? So an example of this would be when we try to compute the limit as x goes to infinity, say, of x times sine 1 over x. All right. All right, so as x goes to infinity, well, x goes to infinity, so the first factor, right, it goes to infinity, times, and then sine. Well, as x goes to infinity, we know that 1 over x goes to 0. Now 1 over infinity is 0 at the limit, on the positive side there. And then sine of 0, sine of something that goes to 0, something that goes to 0. Sine of 0 is 0. So indeed, you get infinity times 0, which is indeterminate. Now, this indeterminate form that we're discussing is, sorry about that, is related to, so this indeterminate form is related to the previous two, right? So if you have infinity times 0, well, again, this is all kind of rough, but we can think of the infinity well, okay, I won't do that one. So just forget that idea for a second. Okay, so what we're going to do, I'll demonstrate the same idea, but with this particular example. We know that if you have x and it's non-zero, then you can write it as the reciprocal of its own reciprocal. Yeah, 1 over x is the same thing as x, right? So for example, 1 over a half, well, half goes into 1 twice, so that's 2. So if you have when you see the indeterminate form infinity times 0, you can always take one of the factors and write it as the reciprocal of its own reciprocal. So we have sine, we're gonna leave that alone. And then the x, we're gonna write as 1 over x. Okay, so now when you try to evaluate the limit, what do you get? Well, the numerator goes to 0 because sine of 1 over infinity, if you will, is sine of 0. And the denominator is 1 over x, so as x goes to infinity, the denominator also goes to 0. So you see that this indeterminate form really can be reconceptualized as 0 over 0. Okay, so now what is this limit? So this is like a pop quiz if you were here yesterday. Okay, well, if we let u equal to 1 over x, okay, we'll get that this expression becomes sine of u over u, right? All I did is replace 1 over x here with u, because we defined it to be u. Now, as x goes to infinity, we know that we already kind of discussed that u will go to 0, yeah? Because u is equal to 1 over x. So we can restate this limit as saying the limit as u goes to 0 of sine u over u. And then you should be able to tell me what this limit is if you were here yesterday. Special trig limit. Yeah, very good. 1. So here, right, we had this kind of indeterminate thing when we try to evaluate directly infinity times 0. But after some algebra, we saw that the limit actually exists and it's equal to 1. Okay. Now, as another example, suppose instead we had x squared times sine of 1 over x. And x is going to infinity. We can always use L'Hopital's rule, just not at the beginning of first semester of calculus. They won't let you. You're absolutely right. If you're familiar with L'Hopital's rule, you're good, easy peasy. But even if you know it, you will not be allowed to use it at the beginning. Okay. All right. All right, so then for this one, when we evaluate directly, we still get the same indeterminate form. Infinity squared, if you will, is infinity, and sine of 1 over infinity is something, 0. Okay. So we can use the same idea. We simply rewrite the x squared as 1 over its reciprocal, so that we get indeterminate form 0 over 0. Okay, and then try to let's see, use our special trig limit. So we can think of this as I should have just done 1 over x. Okay, let's just write this as x times sine xl. Okay. So what is the limit of the second factor as x goes to infinity? Well, we know at the limit that that's going to go to 1, because it's just the previous problem that we did. Okay. So you can get the limit of x times the limit of sine 1 over x divided by 1 over x. And so we know that this will go to infinity, and this is our special trig limit. So you get 1. And what's infinity times 1, do you think? Yeah, that's infinity, right? What's 2 times infinity? It's infinity. Okay. All right. So here we had an indeterminate form, and then it turns out that this time the limit didn't exist. So that's why it's indeterminate, right? In some cases, the limit will exist. In other cases, it won't. All right. So that's my interlude, except that, of course, there's other indeterminate forms. So you'll look at those in detail in your class. This is what we have so far. Other indeterminates form are infinity minus infinity, and you might want to think about why that is. Like, think of examples, okay, where sometimes this limit will exist, sometimes it won't. Also, 1 to the power infinity. Well, an interesting example of that, because we're looking at our superstar function and number, I guess. If you take the limit as x goes to infinity, 1 plus 1 over x to the power x. Evaluating this directly as x goes to infinity, 1 over x will go to 0. And so then 1 plus 1 over x is equal to 1, and the exponent is x, so that goes to infinity. So you get 1 to the infinity. And it turns out that this limit does exist. It's equal to the number e. So that's another thing, if you're curious. But that's an example of that indeterminate form. And you'll learn methods for computing that limit, which are more involved. It has to do with natural log, but okay. All right, beautiful. So that's my interlude about the other indeterminate forms I didn't really mention because I don't want to complicate things too much. Okay. All right, so it's 2 o'clock. We'll be taking a 5-minute break.
I have a quick question, if you don't mind asking.
Go for it.
Yeah.
Go for it.
So for the indeterminate forms, like I didn't understand like what would you what would the final like output be? What would you say is like if you're writing that down on a paper, what would you finally write? You know what I mean?
So if you try to evaluate a limit and you get one of these indeterminate forms,
Yeah,
what to
so zero,
do?
yeah, infinity or infinity, like yeah.
Yeah, well, what you do is, well, first of all, indeterminate form means exactly that you cannot determine whether the limit exists or not. So you have to do something else. So you're going to do some sort of algebra and then try to reevaluate the limit. And then maybe you'll get the answer that the limit either doesn't exist or it does. So after you get indeterminate form, you can't conclude anything. You got to go through this whole algebra business, and you learn a whole bunch of techniques. We covered some of them. And afterwards, you can reevaluate the limit and say, yes, the limit does exist, or no, it doesn't.
Okay. Okay. So L'Hopital's rule is basically another tool, like we'll learn in later, but it's a tool you can use to determine the limit of an indeterminate function.
Which technique? I didn't catch which technique you're referring to.
L'Hopital's.
Oh yeah, you'll be using L'Hopital's later on. Yeah, for sure. That's definitely a good technique. Yeah.
Thank you.
The next topic is continuity. All right. So continuity of a function is something that we define at a point. So we say either a function is continuous at a point or not. Okay. So what does it mean for a function to be continuous at a point? And then guess why does it matter? So so we say f is continuous at a point. If the following statement is true. All right. So that limit statement, limit of f as x goes to a is equal to f at a, encapsulates what we mean by continuity. It's the very definition. Yeah. And really, there are three parts to the statement, three things that you want to look at, right? So if you look at the right-hand side of the statement, f at a, by writing that down, what are you implying? You're implying that the function is defined at a. It has for a function to be continuous at a point, it has to exist there. It has to be defined. That's one thing. Like you can't talk about a function not being continuous at a point if it's not defined. So that's one thing you check for. So f must be defined at x equals a for it to be even have a chance of being continuous. You have to be able to say f of a is equal to this. Right. Now, if you look at the left-hand side of this statement, by writing that down, what you're saying is that the limit has to exist. Otherwise, you wouldn't be writing that, right? So the second thing that you want to make sure is that the limit as x approaches a of the function exists. And recall what that means for us. It means that the limit from the left and the right exist, and they match. The limit from the left and the right. So let me just write that down. That means the limit from the left is the same as the limit from the right. And of course, they have to exist in the first place. Okay. So the function kind of has the same behavior on either side of A. And finally, it's this equality part that we have to consider, this equals. Okay. So finally, even if the function is defined at A, and the limit of the function as x approaches A exists, they have to agree. We have to have that equality. So they must agree. The limit must agree with what the function does at A. Okay. So I guess I could draw three graphs, or three graphs of three functions, all of which are discontinuous at A. And you should be able to tell me the reason. So here's the first function's graph. the second function's graph. And the third function's graph. Now, all these graphs represent functions which are discontinuous at x equals a. Okay. So if we look at the first one, whatever one. So for which reason is this function discontinuous at a? Reason number 1, number 2, or number 3? So graph A, just say A, B, C. Okay. The first reason, right? In the graph, we have this open circle indicating that f at a doesn't exist. Yeah, there is no, if you'd like, if x goes up, it misses the graph, meaning that the function is not defined there. There is no graph. So this is for reason number 1. The function is not defined at a. All right. So can you think of an example that we looked at? Yeah. So let's look at an example of such a function. Sine x over x. Yeah. Is this what's the domain of this function? Well, sine is defined everywhere, by the way, right? X could be anything, and you can stick that into sine. But the denominator cannot be 0. So the domain of this function is all real numbers except 0. So the function is not defined at 0, therefore it cannot be continuous there. Okay. Now, notice that the limit for the first, of course, we're still looking at the first one. We separate these. The limit as x approaches a does indeed exist, right? The limit from the left and the right would agree. But the way the but the function cannot be continuous at a place that's not defined. All right. Graph B. So for which reason is our function not continuous at a? Reason number 2, right? It looks like this dark circle indicates that yes, indeed, if you plug in a into your function, you hit the graph because of the dark circle. So f of a exists. So it's not the first reason. But it's the second reason, because the limit from the left, right, is something. But it's not the same as the limit as x approaches a, but from the right-hand side of a. Not equal to. They're not equal. So let's say that limit is r for right-sided limit. So they're not equal. Okay. So this is for reason number 2. Even though the function is defined at a, the limit as x approaches a doesn't exist in general. The limits are different from either side. All right. And do we know if, have we looked at a function that has this characteristic, I guess? I gotta be careful. Yeah, never mind. Yeah, but okay. So what about the third graph, the graph of C? Is the function defined at A? Sure. Okay. Does the limit exist? Well, sure. The limit as x approaches A from the left is the same thing as the limit as x approaches A from the right. So the limit exists. But it's the third reason, right? Even though the function exists at A and the limit exists as we approach A, they're not equal. So how the function behaves at around A doesn't match what the function does at A. Yeah, so this is reason number 3. Very good. All right. So has anybody given you a phrase or some way of characterizing functions which are, say, continuous or not continuous, either one? Are there kind of, what's the word? Rule of thumbs, I guess. If you look at the graph. Well, it's possible that a function So to answer the question, somebody said differentiable. So a function might be continuous at a point, but not differentiable at a point. So that's a different issue. They're related, but it's different. Okay, so continuity is different than differentiability. Okay. Well, you might have heard that if you a continuous function is one which you can draw without lifting your pencil, right? So if we look at an example of a continuous function, maybe it'll be like at A at least, right? You'll be drawing your graph and you never have to lift your pencil. So that way, okay, f of A exists and the limit is the same, right? As x approaches A, the values of the function approach function at A. So so if you think of the limit as a anticipation, right? And what the function does at A as culmination, then you hope that would be, anyway, okay. Some people say that a continuous function has a graph where you don't have, it's nice and connected. And that's strictly not true, but it's a good kind of way of thinking of it, especially for the functions that you're going to have in calculus, first semester calculus. Yeah, we can definitely like contrive something ridiculous where the graph would in no sense be connected in any sense that we would think a connected graph would look like, yet the function is continuous at a point. I don't know. Do you guys want to see an example of such a function, or you'd rather not? Since you're not going to be really dealing with such anomalies, you'd rather not? Yeah, okay. I was just waiting for that one. Yeah, I apologize. Okay, but here's a example. So, ooh. Do you know? Okay, so if x is a rational number, we can define x to be the function to be 0. So I'm using a piecewise function. And if x is a real number that's not rational, so this is a rational number, x is rational versus x is irrational. We can define the function to be, let's say, 1 over x. Or, sorry, just x. Right, so if you have the graph of this function, right, a bunch of, there's infinitely many points on the number line which are rational, like fractions, anything that can be expressed as a ratio of two integers. So any number expressible as a ratio of two integers. What time is it? Okay. It's called rational. And so there's infinitely many such numbers in the number line. So we define our function to be 0 for every such thing. So you kind of imagine the number line being peppered with these, right? There are holes because between every rational, there's also irrationals, but it's this graph. But for all the numbers on the number line which are not rational, and there's infinitely many of them as well, we define our function to be the reciprocal of that. So what's going to happen if I draw that in orange is you're going to get, or not the reciprocal, just x. So you're going to get this thing for irrational x's. Okay. Right, so this graph is just full of whole. Remember that a graph of a function is just a model for how we visualize a function, but these kind of anomalous functions here, they have the graph are kind of have a bunch of holes so that it's not connected in any sense that would really mean. But at the origin, this function happens to be continuous. So f is continuous. So the moral is that yes, as far as you're going to be concerned in calculus 1, continuous functions have graphs which are nice and connected. You don't have to lift your pencil to draw the graph. But more generally, f could be continuous even though the graph is no in a way that we think is being connected. Okay. Anyway. So now we're going to look at, now where does where does this come into play in your class? What kind of functions will they give you and then ask you, is the function continuous here or not? Well, often you'll see what you might know as piecewise functions or piecewise defined functions. So a piecewise defined function is one which is defined differently depending on what value of x you're looking at. Okay. So for example, we might have, let's say e to the x minus 1, yeah? As long as x, say, is less than 1. And then we might have that for x's which are at least 1 but less than 4, maybe the function is then defined by a different piece. It's defined by the expression 2 times square root of x. And maybe for x's which are at least 4, we can define this to be, let's say, 2 over x minus 5. So depending on the interval that we're looking at, yep, I don't need all that negative space there. So if x is less than 1, right? So if I say, what's f of 0, what would you say? Well, you'd notice that when x is 0, that belongs in that first interval where x is less than 1. So that tells you that our function is defined by the first piece, the first expression, be e to the minus 1. Okay. And if somebody says, what's f at 1, what would you say? Well, you'd see that here the second piece is defined, is used whenever x is at least 1, but strictly less than 4. But okay, anyway, if x is 1, that falls into that and for second interval, therefore we would use the second piece. All right. So you get to, okay. Anyway, just in case you don't know piecewise functions. All right. So, and the graph of each of these individual pieces on its interval is continuous. Each of these is continuous by itself, as it turns out. And where you're going to be looking for problems, well, okay, except this piece, the last piece. Where is this piece not continuous? So I should have mentioned that. If you look at that third piece, where is that? Yeah, at 5. And do we use that piece? Oops. Do we use that piece whenever x equals 5? Yeah. If x is 5, 5 is greater than 4, therefore we would use this piece. But then our function there, that piece is not defined. So right away we see that we have a discontinuity at x equals 5. So since f is not defined at x equals 5, first reason, right? F cannot be continuous there. You can't say that a function is continuous somewhere where it doesn't even exist. It's just a silly, empty statement. Okay. Now, what are the other possible trouble spots? What are the other possibilities? Other possibilities for when we have a break in the graph of our function? Well, that could happen as we go from one piece of our piecewise function to another, right? Nothing says that if you graph this piece on its interval and then this piece on its interval, you'll have a connected graph. So automatically, the other places we look for discontinuities are exactly at the transition points as we transition from one interval to the other. Okay. So we have to consider what happens at x equals 1. We have to ask the question, is our function continuous at x equals 1? And then we have to ask the question, is our function continuous at x equals 4? Those are two possible those are two possible places where our function is discontinuous. Okay, so how do we check? Notice I haven't provided you a graph yet, because that's the whole point. With a graph, you could answer the question right away. Well, so we're going to ask ourselves, is f continuous at x equals 1? That's a question, right? So then you look for you check the three statements, right? So you check the three conditions. Well, is f defined at 1? Sure. F at 1, when x is 1, we get that f equals 2. So yes, right? The function is defined at 1. Does the limit exist? Well, how do we check whether the limit exists? Well, we check the limit from the left. So we're going to approach 1, but from the left side of the number line. So we use that negative superscript of your function. Okay. Now tell me, if x is approaching 1 from the left, which piece of our piecewise function would we use? The first, second, or third piece? Well, yeah, the first piece, yeah. Because if x is approaching 1 from the left, x is going to be smaller than 1, even though it's getting close to 1. So obviously that's the first interval, so we would use the first piece. So with a piecewise function, you're going to be expected to determine, you know which piece to use depending on which side of your contentious point you're on, right? So we use the first piece. And this limit you can just evaluate directly. We get e to the 0, which is defined, this of course is 1. All right, so now we check the limit as x approaches 1 from the right. So obviously now x is slightly bigger than 1, but close to 1, right? So clearly we're going to be in this interval, in the second interval. Therefore, we would use the second piece to define for our function. The second expression defines our function there. And so you would get, evaluating directly, you just get 2. Okay, so does the limit exist? The limit from the left is 1, but the limit from the right is 2. So the two one-sided limits do not exist. Very good. Therefore, the limit does not exist. So limit as x approaches 1 without saying which direction in general does not exist. So then we see that the second condition doesn't hold. Therefore, f is not continuous at 1. So the answer is no. And now the third condition is really not really applicable, right? Because if the limit doesn't exist, you can't compare the limit of the function to what the function at 1. Okay. All right. So the next contentious point where we possibly have a discontinuity is x equals 4. So is f continuous at x equals 4? Well, you'll go through the same rigor more, but okay, the same process. Sorry, same procedure. So is the function defined at 4? Well, heck yeah, right? So when x equals 4, what is the value of our function? Oh, I see what happened. Yeah, that's fine. So 4, -1. 2, 4. Yeah, I apologize. I actually miswrote one of the. I'm just going to change this to -4. My apologies. Okay, so I just miswrote something when I wrote this function down. This should be a -4. Okay. Okay. Right. So is the function defined at 4? It's not. So remember that we said that this third piece is used for whenever x is at least 4. So look for whether you have a strict inequality like x, here x is strictly less than 4 as opposed to over here where x is 4 or more. So yeah, the function is defined at 4 because when x equals 4, right, we'd be using this piece. So that's equal to 4. So yes, the function exists at 4 and it's equal to 4. Oh, okay, I apologize. You didn't say no to that. Okay. So something other. I gotcha. Oops. All right, so then you go on to the next condition, and you ask yourself, does the limit exist as x approaches 4? Well, for that, you want to compute the limit as x goes to 4 from the left, in which case you would use the middle piece, because x is close to 4, but slightly to the left, or less than 4. And you get that evaluating directly, of course, this is just 4. And the limit from the right will be the same. This time, of course, we'd be using the piece with the last piece because x is greater than 4. So right, so indeed you get a 4 as well if you evaluate that directly. So the limit does exist. Right? The limit as x approaches 4, regardless of side, is 4. Okay, so finally, the function is defined at 4 and the limit is 4. So do those match? So you finally check whether the limit equals the function. Yes, yeah, the limit as x approaches 4 is the same thing as what the function does at 4. Okay, so yes. So the answer, yes, would be yes, the function is continuous at x equals 4. All right, good. I guess if I graph this function, it would look something like you have an exponential. I would use an open circle because that exponential is only used when x is strictly less than 1. And then you have some kind of translated in scale or just scaled square root function. Perfect. And then you have some kind of yeah, so that would go up and this would go down. Perfect. Okay, so that would be what the graph might look like. So I guess that's another. So notice the jump discontinuity here. Notice that our graph is connected at x equals 4, so continuous, like we concluded. And then we have a vertical asymptote x equals 5, and so as soon as you have a vertical, well, I won't say that. Okay. But our function is not defined at 5 since it's discontinuous there. All right. Now, continuity is an important property, I guess. It allows us to evaluate limits easier. So, yeah, okay. Anyway, it's an important property. So let me move on from continuity because we might have time for epsilon-delta. Yeah, you have any questions so far or anything you're interested in regarding continuity? All right, so this is a tough topic, I guess. All right, so first of all, the Greek alphabet, right? How far do we know? How far can you go? How many letters of the Greek alphabet do you know? So you have alpha, boy, yeah, alpha, beta, gamma, oops, delta, epsilon. So like, if you'd like the corresponding, I don't know if that's A, B, I don't know about gamma, maybe C. Delta is like D, epsilon is like E, say, yeah. So alpha, beta. Now, if anybody's joining some kind of Greek life thing, yeah, you'll know these probably. And now, why do we use these Greek letters in math? Well, because they ran out of letters in the Roman alphabet, right? And then they kind of, at least European mathematics, right? They kind of look back at Greece. So they used Greek letters. All right. Now, here in the context, we're going to use the epsilon delta definition of limit. So epsilon delta will represent positive quantities. So we'll write the delta as a positive quantity, and so is epsilon and delta are both positive quantities, so greater than 0. All right. So when we look at a limit existing, and I guess I should actually draw the circle there, open circle. Because with limits, remember, I don't care what the function actually does at A, only how it behaves around A. All right. The idea is that if we do have a limit, like we can see in this picture, we have a limit. Let's call that L. And you would write that, yes, limit as x approaches A of our function. This is the graph of our function, is equal to L, right? Okay, and so if we try to articulate that, what we're saying is that regardless of how close I want f of x to be to this limit, right? So I want f of x, so if we want, let's see, what's the word? So if we want f of x to be close, and that's going to be a keyword, to the limit, as we expect it should be, yeah, then I guess we can always find x's that are close enough to A. We can always find some x. We can always find x close enough, again, that word, close, so that happens, right? So if you want you want f of x to be like a centimeter away from your limit, you can always find some x value close to A, such that if you plug that x value into your function, your f of x will be within the target range, I guess, close enough to L. Okay. Now, we want to kind of make that better, right? So what we can say to make that, because that's still very loosely speaking. So what we're going to do is when we say that we want f of x to be close to L, we're going to specify that, let me redraw that. So if you want f of x to be close to L, we're going to say that there's a range. We want f of x to be within some distance of the limit. And that distance is going to be epsilon. Okay. So epsilon denotes a distance on the y-axis, a distance away from the limit. Okay. So in particular, if you start with the limit and you add epsilon, you end up with the upper endpoint. And if you start with the limit and you subtract the distance epsilon, you end up with the lower endpoint. Okay. So now when we say that we want f of x to be close, right, to the limit, we mean that we want f of x to be in that interval. So f of x will have to be between, or it has to be more than L minus epsilon and less than L plus. So between these two endpoints, yeah? F of x has to be in that interval. All right. Okay. And now this, okay. And epsilon could be any distance we want. So given any positive quantity we want, f of x to be in that interval, that's between L minus epsilon and L plus epsilon. So can we find an x that's close enough to A? So what do we mean by, so can we find some interval? Can we find an x close enough to A? So by saying that x is close enough to A, let's just suppose that it's within a distance delta. So that's that other distance we were talking about. So delta is going to be a distance that you're going to associate with the x-axis. So can we find an x, or I guess I should say, can I get close enough to A, so delta close, such that f of x, or x, being in that interval, implies that f of x will be within this interval on the y-axis. So we want x to be between A minus delta and A plus delta. Okay. So can we find a distance such that if we know that x is within that distance of A, you plug that into your function, then it's guaranteed that f of x will be within a distance of epsilon of the limit. All right. So now what we do is formalize this. So if I say that f of x is between these two numbers, I can subtract the limit from everything. So minus L, minus L, minus L. This is f of x minus the limit is now between negative epsilon and positive epsilon. Yeah. Okay. And there's another way of writing that, right? If, just in general, if you have a quantity which is like between -4 and +4, what's another way of describing that, or another way of writing that same inequality using absolute values? Well, if k is a quantity between -4 and 4, we can say that its magnitude must be less than 4. Okay, so that's going to be to say that a number is between right. So to say that this quantity is between negative epsilon and positive epsilon is the same That's to say that the absolute value of f of x minus the limit is less than epsilon. Okay. And this, the mature way to interpret this absolute value is to say distance. You get absolute value of a minus b really is the distance between 2 points on a number line. Distance between a and b. Okay. So what this is telling us is that the distance between f of x and the limit is less than this epsilon. Okay. So likewise, if I take this inequality, and then we subtract a from everything, and we'll get to the definition. This is just kind of building up an intuition of what all these symbols might mean. Then this is equivalent to saying that the absolute value of x minus a is less than delta, which is saying that the distance between x and a over here is less than delta, right? The distance is less than delta. Okay. So now we can write down the definition of a limit existing. Whenever we write this, we mean that for any epsilon you choose, so that regardless of how close you want to get to the limit on the y-axis, it has to be positive, of course, we can always find a delta, so a distance on the x-axis, such that, okay, if, right, x is close enough to a, delta close, so that is to say the distance between x and a is less than delta. And I'll say technicality, I'll say that's greater than 0, because remember, what would it mean for the absolute value of x minus a to be equal to 0? What does that mean? Well, that's the same thing as saying that the distance between x and a is 0. So wouldn't x have to equal to a? Yeah. But remember, with limits, we don't care. We don't consider what happens when x equals a. So that's just a technicality. So if x is close enough to a, delta close, then it's guaranteed that if you take that x and you plug it into your function, how far will it be away from the limit? Well, at most epsilon. Yeah. So this is actually a definition of this limit here. So this is the definition. So for any epsilon, there exists a delta such that if the distance between x and a is less than delta, then it's guaranteed that the f of x, then the distance between f of x and the limit is less than this arbitrary epsilon. So that's a pretty abstract definition. But you can see what it does, right? As you want f of x to get closer and closer to L, you're going to force x to be closer and closer to a. Okay. Right, but just so you don't get shocked when you see this in class, right? Just remember epsilon delta are distances associated with the y and x axis respectively, and or lengths, if you will. And then the absolute value of x minus a is really saying distance between x and a, and likewise for f of x and L. All right. So suppose we want to find the limit or prove the limit of, let's say, 3x minus 1 or minus 2 as x approaches 2. Oops. Well, we know how to compute this limit. What is it? It's 3 times 2 minus 2, so 6 minus 4. Okay, so you're going to get the statement, and they're going to say, well, if I give you, let's keep it simple. If I give you epsilon, well, so given an epsilon, and they might give you a number, or they just might leave it as epsilon. Find an appropriate delta such that the limit definition is satisfied. So it's going to be a problem, semester 1. So you're going to say, well, given this epsilon, I have to show that there exists a delta, right? Delta. So I'm going to simply define it into existence. Let delta equal, and this is the crux problem. How do you define delta appropriately? Well, the criteria for defining delta is right over here, right? So if we know that x minus a, so what is a in our, so what is a and what is L in our problem? Well, a is the number that x is approaching, and L is the limit. And our function is 3x minus 2. So if we know that the distance between x and 2 is less than delta, without knowing what delta is, we would want, right, that once we plug in x into our function, we want this f of x to be epsilon close to the limit. The limit is 4. This is what we want to be true. And so what we have to do is we have to choose delta so that we get what we want. All right. All right. So I guess let's start with what we want to be true. So what's f of x? Okay. And what's the limit? It's 4. And we want this to be less than epsilon. So now you're just going to simplify that, and notice that now you can factor out a 3. Which is interesting, and of course the absolute value of 3 is just 3. Now what's the magic? Well, notice that we have this, apologize. We have this absolute value, this x minus 2 over here, correct? The absolute value of x minus 2. And we see that over here as well. So let's divide both sides by 3 over here. Now we see that the absolute value of x minus 2 must be less than epsilon divided by 2. So how do you think we should define our delta if we compare these two statements? Well, we should probably let delta be epsilon divided by 2. So we're going to let delta equal to epsilon divided by 2, okay? And that should be a sufficient delta. And we can maybe prove it. So we have that. It's really just a repeat. Here. So we have our function minus the limit, okay? That's equal to 3x minus 6, factor out 3. So now we know that the absolute value of x minus 2 is assumed to be less than delta. So this is going to be a little tricky, but we're going to leave 3 alone, but replace this factor with delta, which we know is bigger. So the whole expression is bigger. But then delta we define to be epsilon divided by 2. So this is equal to 3. Wait a minute. Oh, that should be a 3. Okay, my bad. I apologize. I divided by 3, and so I should let delta equal to epsilon divided by 3. Okay, so delta is defined to be, we defined delta, I should say, to be epsilon divided by 3. And then indeed, there you go. The 3's cancel. And then what you have is your function minus the limit is eventually less than epsilon. And that's what you wanted. So I think that's a, gosh, complicated note to leave on. All right. So I don't know if that was wise, but at least you know some of the Greek alphabet, right? You kind of know what epsilon delta mean. Yeah, please go ahead and give us your feedback. Yeah, so calculus, we use simple things like lines, polygons, some limiting process limits. to learn something about more complicated things. And limits were very important. They were used to define actual derivative, which is the slope of a tangent line to your function. And there are some abstract definitions that you might have to deal with, like epsilon-delta. Yeah, we hope to see everybody on campus. I mean, fingers crossed. The tutoring lab, the Student Success Center, their peer tutoring lab is in the basement of the library. We're going to open the second week of classes, so we won't be open the first week. Just come by, say hello, ask questions. We should all be good. Thank you for taking your time to be here.